Para gravar, vocês depois costumam disponibilizar
Sim,
externamente?
sim. Depois costumamos disponibilizar. Pronto. Já te fiz host novamente. Isto nem perdeu o share screen, portanto. Está tudo. So, hello everyone. Welcome to today's lunch seminar. Let's just wait a few more minutes so that more people can join us, and then we'll start.
O ruído de fundo vem de mim. Eu
Uh,
posso trocar de fones se eu preciso.
Pois.
Posso experimentar fazer mute a ver se termina.
Eu não estou a ouvir muito, mas pode ser.
Eu vou experimentar fazer mute.
Ok.
Ver se
Sim. Sim, vem do teu lado.
Tenho só um minuto para trocar de fones.
Ok. Ok. Eu não te estou a ouvir. Não sei se. João? João? João, consegues ouvir-me?
Está melhor agora?
Sim. Ok.
Ok.
Sim.
Boa.
Consegues ouvir-me? Está tudo
Sim,
bem?
sim, ótimo.
Ok,
Sim.
então vamos se calhar começar. Let's get started. Hello, welcome to Priberam's lunch seminar. My name is Ruben, and today we have with us João Gante. João Gante will tell us about his work. Can 5G and machine learning replace the GPS? So João Gante is a PhD candidate at Técnico. He researches machine learning-based algorithms for positioning and tracking with 5G technology. He is supervised by Professor Lionel Souza. João is also currently a machine learning engineer at Templar in London, where machine learning is the key to predict the outcome of large construction projects. So without further ado, let's get started. João Gante.
Yes, thank you, Ruben. So as Ruben said, I'm a student at Instituto Superior Técnico. I'm currently waiting to defend my thesis, and this talk is about the second half of my work. And the talk is titled, Can 5G and machine learning replace the GPS? The talk has the standard format. I'll go through an introduction so everyone is on page about what exactly I tried to implement during that second half of my PhD, and then we'll talk about some conclusions. So let's first talk about positioning. Everyone knows the GPS. I suppose that you use the GPS nearly every day, although maybe now with the lockdown it's a little bit more tricky, but it's still a very important piece of technology. However, that's not the most correct name for it. The most correct name is the GNSS, which stands for Global Navigation Satellite Systems. And to give you an overview, it was launched in the 70s, initially only available to the military, but it became available to the public in the 1980s. By now, there are many GNSS systems. So the United States has the GPS, Europe has Galileo, there is one for Russia, one for Japan, etc. But they have all the same basics. So they all work with multilateration of time of arrival samples. So from the time of arrival between the GPS satellite and your mobile device, you are able to infer the distance, and from multiple distance, you can get a position estimate. This signal is in fact a pseudo-random sequence between 1 and 10 million chips per second. Chip is a symbol in telecommunications, but you can roughly think it about as bits per second. Not the same thing, but you can think about it as bits per second. The old systems work mostly at 1 million chips per second, but the new systems, and there are currently satellites being deployed, expect to work mostly at 10 million chips per second. And as you can imagine, the quality of the prediction depends a lot on the frequency of the signal, more specifically the bandwidth of the signal. And the average error on common devices, such as our smartphone, our smartwatch, etc., is about 3 meters. There are specialized devices that can get much lower error. There are military devices that can get even lower error, but as a rule of thumb, you can imagine that a normal GPS device has an average error of 3 meters. But this talk is about something that tries to go beyond the GNSS, so it must have limitations. So I want to convince you that there are a few problems that should be addressed. So firstly, it is a system where synchronization is very, very important. To have an idea, before you are able to get a position estimate, you need to have 3 pieces of information. The first one is the almanac, which is the global status of the GNSS system. The second type of information is the ephemeris, which is the information regarding the orbit of each satellite. And lastly, you need to have timing information, so information about the atomic clock in which each of the satellites. And when the GPS was first launched, you needed to wait 12.5 minutes before you could get a position estimate. That's a lot of time. More recently, there is a technology called assisted GNSS, although it's more commonly known as assisted GPS because GPS is the most commonly used word for this. And with the assisted GNSS, the base station of your cellular system sends to your mobile device the almanac and the ephemeris. So you only need to wait 6 seconds until you are able to get a position estimate. The second type of problems is concerned with the signal quality itself. As you can imagine, this is a communication between a satellite device and a mobile and a device on Earth. So it's a very complicated communication environment. There are many, many sources of noise. For instance, the clocks should be perfectly synchronized, but it's very difficult to do in practice. There are atmospheric effects that change over time, etc. To give you an idea of how complicated the communication channel is, there is a Wikipedia page dedicated to sources of noise in GNSS systems because it's a very complicated environment. Moreover, it's very complicated to increase the signal bandwidth. And by this, I mean that a satellite system uses a spectrum throughout the whole world. And spectrum is a very, very valuable resource. So because it has such high competition, it is not feasible for localization systems, GNSS systems, to increase their bandwidth. And the bandwidth is in turn related to the quality of the estimate. To give you an idea of how expensive bandwidth is, this is a table with auctions for 4G networks in the UK alone in 2013. So in 2013 alone, in the UK, £2 billion were spent just to acquire some bandwidth. So it's a very, very expensive resource in general. More limitations. It's very hard to get sporadic measurements. So imagine you want to have a system that gets a position estimate once every hour, maybe to help you track your kid so your kid doesn't get lost or something like this. But this is very difficult to do in practice with low power consumption and high quality estimates. This is because the minimum latency is 6 seconds because of the reasons I've talked before. So it means that your GPS antenna has to stay on for at least 6 seconds before you are able to get some decent estimate. Moreover, good estimates come from tracking, so you need even more seconds in order to get a decent estimate. In practice, it means that every time you want to get some measurement, you need to spend a lot of energy, and this is a very high lower bound, which is very undesirable. But there are more problems. For instance, it requires a specialized set of receiver antennas on your mobile device. It does not work underground, and it has very poor performance in urban canyons. By urban canyons, you need to think about cities like New York City, where a street is surrounded by very tall buildings. Usually, those type of environments have very bad GNSS performance. Moreover, there are satellite problems. Satellites can cause space debris. Satellites are most susceptible to solar storms. If you notice, if you pay attention to the news and if you can catch in advance that there is going to be a solar storm, you will notice that during the solar storm, your GPS is very, very fuzzy. It has much lower performance. So what can we do about it? This image is taken from a survey from 2018, and it has an overview of what is expected of positioning systems for 5G. So on the x-axis, you have the error. On the y-axis, you have the type of positioning environment: indoors, outdoors, in urban scenarios because of those urban canyon problem, and in rural environments. In fact, you can see that there is this shade of red below an error of 1 meter, but this is expected to happen. We still don't have this in practice. So it's very hard to obtain errors inferior to 1 meter with commercial systems. There are alternatives. For instance, you have this orange bit, which corresponds to getting positioning directly from your base station. If you have multiple base stations, you can use the green one, which are techniques that use time difference of arrival. But in practice, it's very hard to operate in this region. And what I'm going to talk about later in this presentation, it's about this region. So I propose something that is meant to operate in this region. But to understand it, we need to understand the 5G. And to understand the 5G, we need to understand what the 5G is not. The 5G is not a cause of COVID, nor a cause of brain tumors or anything like that. It is a big source of conspiracy theories, but if you are able to look past that, it is a great piece of technology. So firstly, it contains improved under 6 gigahertz communications. What is this? You know the 4G and the LTE systems. The 5G is an improved version of that, but not only that, it also introduces for the first time cellular networks that operate above 24 gigahertz, and these are called the millimeter waves, which are the focus or part of the focus of this presentation. By now, you are probably asking yourself, why the sudden interest? Why didn't we operate with more than 24 gigahertz in the past? And why do we want to do it now? What's the big deal? To give you an idea, let's consider this simple scenario. In dark gray, you have buildings, light gray, you have the streets, and you have multiple mobile devices and a base station. In previous networks, if the green device wanted to communicate with the base station, it can safely assume that it is probably going to be able to communicate through the building, so a direct path between the device and the phone. This is for older, under 6 gigahertz communication systems. When we talk about millimeter waves, this happens. So as you can see, the radiation reflects on most visible objects, obstacles, and it makes the communication environment much more complex. So why do we even bother to try to fix this problem? It looks very, very complicated. This picture is an overview of the radium spectrum allocation in the United States. You have many rows. Each row is in a logarithmic scale, and the end of a certain row is the beginning of the following row. And each row is a order of magnitude. You can see that you have the AM radio here, your cellular networks over here, your Wi-Fi here. But what I want to bring to your attention is that this big blue shade has the same bandwidth as this tiny blue shade, because remember, the x-axis is on a logarithmic scale. So this 60 gigahertz band alone contains more bandwidth than all signals that we are used to. So it is a very, very big opportunity for bandwidth, and we can do all sorts of things with more bandwidth. So I want to talk about two key principles about millimeter waves. There are many things that happen with millimeter waves, but there are two key principles I want to keep you in mind for the rest of this presentation. The first principle is how the propagation happens. There are three important pieces of information to keep in mind. If you imagine this image on the left contains a transmitter and a receiver, the blue line is a standard line of sight communication path, and the green line is what could happen with millimeter wave networks. So firstly, we know that we have higher attenuation. So even this blue path, if you are operating in the millimeter wave regime, will have a much higher attenuation. So long range communications become very, very difficult. Secondly, there is the obstacle interaction. So you can have the green path where things reflect on certain obstacles. And when it reflects, you can think of as the same signal, but with attenuation and delay. And thirdly, you can have massive MIMO, which stands for massive multiple input, multiple output. What does this mean, massive MIMO? In antenna theory, you know that the physical size of a certain antenna is proportional to the communication wavelength. So with millimeter waves, you have a smaller wavelength. Therefore, you can have smaller antennas. But if you think about a mobile phone, it has roughly the same size. You don't want it to shrink that much. So you can, in fact, you can have more antennas using the same physical space. And having more antennas is very important, because when you have multiple antennas, you can apply a signal processing technique called beamforming. What is beamforming? So if you think about the many antennas, imagine a square array of antennas. If you tweak the power gain and the delay of the signal in each individual antenna correctly, you are able to, instead of having an omnidirectional communication, you can have a very directed communication. So you can focus your signal. In telecommunication words, it means that you can add directivity to your signal. Moreover, this all happens electrically, so there are no moving parts. So it's very easy to operate as soon as you have the proper techniques in place. And it allows a third thing called spatial multiplexing. So you remember that I've said that we have a much higher available bandwidth with millimeter waves, but now we can also focus our signals. If we are able to focus our signals, it means that we can put the radiation where we want the radiation to be. So it also lowers the interference of the communications if done properly, which is a whole research area on its own. But you have the possibility of having the same signal with much lower interference between users, which allows you to reuse the spectrum more effectively. So you have more spectrum and you can reuse it better. So there are many sources of gains. And this is why 5G is so important for telecommunication systems. By now, we have all the principles we need to start talking about what I've developed during the second half of my PhD. So when I started looking into this problem about 3 years ago, this was the state of the art. There are two types of positioning methods. There are the methods that are based on some time or distance measurement. So they rely a lot on the geometry of the space. But now with millimeter waves, things reflect everywhere. So it's, unless you have line of sight between your transmitter and your receiver, it's very hard to get reliable time or distance measurements. And the second class of algorithms are called the fingerprint algorithms. And they are called fingerprint algorithms because they consist on measuring some signal in multiple positions in space. And for each position in space, you have the signal and the point in space where you measure that signal. So it's pretty much a standard supervised learning dataset. The problem is that when I started looking into this question, all methods required multiple anchors. By multiple anchors, I mean that you needed to have many, many base stations in order for this to work. And if you recall, millimeter waves do not work in long distance communications. So unless you have a very high density of base stations, this would never work. So the first type is impossible to do, and the second type is impractical to do. So what can we do about it? I started with one assumption. In the propagation environment, most obstacles are immutable. There are people on the street, there are cars on the street, and they move around. Those are not immutable. However, the 5G communication posts or any cellular network communication posts are usually placed in very high positions. So the signal is mostly transmitted from a high position to a low position, and they don't encounter many of the obstacles in practice. They can encounter, but the majority of the obstacles that they are found, they are static. Therefore, if you stand at a certain point in space and measure the signal today, and if you go there tomorrow and you attempt to measure the signal again, the odds are that the signal is roughly the same. So as a consequence, and these are going to be a lot of words and a lot of information, but I'm going to deconstruct these in the following slides, so don't worry. In practice, we can measure a power delay profile. So how the received power changes over time for certain transmissions. And those transmissions can be made more focused with beamforming. This is the nuts of what I've proposed. And then again, I know it's a lot of information, but I'm going to deconstruct this, and we're coming back to this slide a few minutes from now. So let's keep in mind the two basics. We need to take into account that with millimeter waves, things reflect on obstacles, and that we can apply beamforming. With this, we can build an analogy. Most of you probably know about LiDAR, which is what is represented on the GIF on the right of this slide, and it operates through the reflection of light. And because you know that they have the spinning thing on top of mobile devices, and it is able to construct a very accurate image of the surroundings of the car. So let's do an analogy between the LiDAR and what I'm proposing. So firstly, LiDAR reflects on things. It is able to measure things because they reflect back, and is able to recover the same information. With millimeter waves, we also have the reflections. Previously, we didn't have the reflections, but now we have the reflections. Secondly, you know that they have the spinning part of the LiDAR on top of the car. It means that for each point in time, the LiDAR is only collecting information with respect to a certain subset of the space. And with beamforming, we can also do that. We have angular specificity because we can aim the radiation at a certain point of space at a certain time. And thirdly, we want to capture information about distance, so we do sampling in the time domain. That's why you can see the distance in your LiDAR system, because it knows the delay between the transmission and the received signal. However, you can get an analogy between LiDAR and what I'm proposing, but there is a very important distinction, which is in LiDAR, the transmitter and the receiver are in the same place. What I'm proposing is that the transmitter is static, but the receiver could be in any point in space. So there are many points that you can make an analogy to LiDAR, but this distinction is very, very important. So let's come back to the previous slide. So What I'm proposing, and pay attention to this part at the bottom, is that we can get a power delay profile, so a signal over time, and we can use beamforming to increase the spatial resolution. And because of millimeter waves, things will reflect around, and by reflecting around, they interact with the objects. Therefore, there is latent information in those interactions. So in theory, we can use this signal to try to obtain a relative position estimate. So the position relative to the base station. The base station, by its turn, is able to know its absolute position, and if you add the two, you can get an absolute position of your mobile device. This signal is called beamformed fingerprints. So again, the system works roughly like this. You have a certain base station that will transmit a sequence of beamformed signals, and your mobile device will be listening and sampling those signals over time. And the mobile device knows that when the base station is transmitting the beamform pattern 1 and when it is transmitting the beamform pattern 2, etc. So it is able to build a coherent version of that signal. Then the mobile device uploads the data to the base station. The base station has a trained machine learning model. It runs inference, and then it sends back to the device. This upload part and computing the inference at the base station is optional, and I'm going to talk a little bit about it later in the presentation, but for now, consider it like this. So I built this, and my first approach was the naive approach. So let's build a simple neural network and see what comes out. And it turns out that if you apply an MLP to these, you don't get very good results. I got average error of about 10 meters. So it will not even scratch the surface of what GPS could do. So I had to go back to the drawing board, and I needed to study more about millimeter wave communications and observe what was the signal. And if I plotted the signal in a certain way, so if I plot the signal with the x-axis being the transmitter beamforming index and the y-axis being the time domain, so the sample over time, where the top is as index 0 and the bottom as it corresponds to a later point in time, you get this shape. And with this shape, you can notice several things. Firstly, the signal is mostly sparse. This is a standard sample. Most of this region is usually empty, but not always. Sometimes there are values here, and those are very, very important to locate your system. Secondly, you can notice voids. So you can see that the information as lines on the X domain. This happens because if you go to the millimeter wave books, they tell you that the radiation arrives in clusters. So usually the radiation arrives in bundles, and there are very noticeable gaps between those bundles. So if you are able to measure them, if you are able to sample your signal at a good enough speed, then you are able to notice these voids, and these voids contain a lot of useful information. Moreover, the transmitter indexes are not placed randomly, so they correspond to a sweep over the azimuth. So it means that two neighbors have a certain overlap. That's why you see lines on over the x-axis, because it is very likely that the next beamforming index contains overlapping information. And if you look at this is an image, and you know what we can apply to images, convolutional neural networks. It's the basics. So I decided to build this architecture where I apply the convolutional neural networks over the received signal. And with the convolutional layer, we are able to capture information about sequences within each sample. So over the y-axis, we are able to capture information with respect to time, and over the x-axis, we are able to capture information with respect to what happens when between two neighbors beamforming indexes. This is different to what we do in images, in the sense that for images, the two axes have the same type of information. Here, the two axes have different types of information, but it still works very well. However, the results I got from these, which were about 5 meters, if I'm not mistaken, are still not good enough. So I had to keep looking. The next stage was, what is the structure of the signal that you are able to measure outdoors? Firstly, you know that adjacent positions are expected to have very similar input signals. However, there are big discontinuities. So if you think that you are walking on a street and then you decide to turn, you are probably going to be blocked by a certain building. And remember, things reflect on obstacles. So you are going to observe a very different signals. So this means that there is a very strong spatial structure, and maybe you can do something about it. My solution to this was to apply some hierarchical model, where the first part of the hierarchical model was concerned with detecting what is the region of the space that we are now. And the second part of the hierarchical model was trying to obtain a fine-grained positioning estimate from the high-level area region. And the architecture is a bit more complicated to observe visually, but it goes roughly like this. So first you have a classifier. The classifier tells you in what part of the space you are. And then for each classifier, you have a specialized regressor that is able to give you some position estimate. And the idea is that the first classifier, through the discontinuities, is able to detect what is the region of the space that you are operating on. And the fine-grained classifiers, the idea is because you are giving more resources to the model and you are dividing your data set so that it's such that each specialized regressor only sees a specialized part of the data set. So you can invest your resources into giving finer-grained predictions. And the result was positive. But before we can talk about the results, we need to talk about the simulation apparatus, because simulating things in telecommunications is a whole science. Firstly, most telecommunication systems are simulated through channel models, but channel models do not capture very well the reflection part of millimeter waves. So I turned into ray tracing systems. Ray tracing systems are usually used in computational graphics, but they can also be adapted to telecommunications because it's also radiation. And I used a very detailed 3D map from New York City that where scientists at NYU actually did field experiments with millimeter waves. And I replicated their antennas, their whole process. And first I tried to observe if my simulation environment obtained the same results that they obtained in practice. And green light, I got the same results, which are these symbols. So I decided to carry on with the experiment. So this uses a 24 gigahertz frequency, so it operates in the millimeter wave regime. It uses ray tracing on an accurate 3D map. It's very important that it's accurate because the shape of the buildings really influence what's going on. I used a beamforming codebook with 32 elements. This means that I had 32 beamforming elements. This blue arrow is the central position, and you can visualize it as the arrow slightly turning to the left or to the right. This is an area with 400 by 400 meters, which is what is expected for a 5G base station that operates in millimeter waves. And I obtained samples that are 1 meter apart to each other. The last piece of information, which is probably the most important here, is that I sampled at 20 megahertz. This is more than the GPS systems, but remember, we have more bandwidth, so we can have budget to do it in practice. This beamformed fingerprint in total takes much less than 1 millisecond to obtain, so it's very fast. So we can start to see a big difference because the GPS needs at least 6 seconds before it is able to give some position estimate. And I'm telling you that I'm able to capture a signal and I only need less than 1 millisecond to obtain that signal. That is a very big difference. So let's see results. With that hierarchical system using binary data, and by binary data, I mean that if you look at the beamforming fingerprint, you have the power scale. So this is a floating point data. I just applied simple signal detection. So whether each point had a signal or it didn't have a signal. So it's a very simplified version of this data set. Why? Because in practice it's impossible to measure this signal with very high resolution. So I went with the simplest you can do, whether the signal exists or not. And the results were very positive. I got an average error of 4.73 meters. The root mean squared error, which was the metric used in the previous state of the art, was 35 meters, and the thing I developed as a root mean squared error of 19.7 meters. However, if you go look into their paper, they cheat a little bit in their simulations, but I got better results, so I'm not even mad at that. In this plot, we can see that the estimates error per position. And we can see that even in non-line of sight positions, we can get a good positioning estimate. So we are able to do what the previous systems weren't able to do, get good estimates in non-line of sight positions. So in summary, we can get a position estimate whenever there is millimeter wave coverage, which is great. Non-line of sight is not a constraint. We only use a single base station. So if you have more base stations that can provide information to this region in space, you can get a richer signal and therefore better performances. And it requires no additional hardware. So if the system is able to do millimeter wave communications, you will be able to compute this signal. Whereas if you want to use GPS, you need a dedicated antenna. But at this point, I noticed that what GPS does in practice is tracking. So they use Kalman filters, etc., to get much better position estimates. So I decided, well, let's try to do some tracking here. Why do we want to do tracking? Firstly, there are physical constraints. So objects have limited velocity, limited acceleration, etc. Secondly, there are man-made constraints. There are traffic rules, there is space segmentation, and by space segmentation, I mean that a boat can only go in the water, a car should only go on the streets. So it is a very segmented region. And thirdly, it improves the signal robustness, because if you look at the 95th percentile of the cumulative histogram a few slides ago, the maximum error was very, very high, because the system was simulated with noise, and when noise kicks in, it ruins the predictions. And if you are able to track, then you are able to capture many samples and you can recover from noise spikes. Can we do it? Well, the beamformed fingerprint only requires 1 millisecond to obtain, so I saw no reason not to do it. The first thing I attempted to do is Lstms, because let's face it, they are the bread and butter of recurrent models. Thinking at a high level, it has everything I needed. So it is able to keep short-term information, speed, direction, etc. And with the gating from Lstms, you are able to keep the whole estimate in perspective. So you should be able to know whether it is a car, a pedestrian, etc. But I was not entirely happy with the results, so I tried a second thing, which are the temporal convolutional networks. The temporal convolutional networks, long story short, they apply a convolution in the temporal domain, and convolutions are very well known to signal processing, and being someone that comes from a signal processing background, I really like convolutions, so I decided to attempt it. Also, they are used in some known networks. For instance, the DeepMind's WaveNet, which synthesizes sound, is made through convolutions in time. Not with temporal convolution networks, but with a similar thing. These temporal convolution networks have an important distinction to normal convolutions in the time domain, in which they apply dilated convolutions. So they have blocks, and the further away you are from the output, the more dilated are the convolutions. So if you see in the first block, it captures, it has a dilation factor of 1. In the second block, it has a dilation factor of 2, so it captures the sample from the previous layer and a sample from 2 time samples ago in the previous layer, and so on and so forth. So you can increase the scope of your convolutions with manageable complexity without losing too much information. Also, they have residual connections which help to stabilize the network. To simulate this, I needed to add some extra apparatus because previously I was dealing with a single position, and I'm dealing with sequences of position. So I had to synthesize movements. I had to create 3 types of synthetic movements that I think it represents the common use cases. I assume that we could have static users, we could have pedestrians, or we could have vehicles, and the movement is roughly what is plotted on the left. And those are bundled in together. This is a table with parameters, and if we want to, we can discuss them a little bit, but other than the average speed from a pedestrian, I couldn't find relevant information. So I tried to use a rule of thumb. And I assumed that I was gathering 1 beamformed fingerprint per second, which is what many commercial GNSS systems do in practice. They are able to update the results once per second. Firstly, comparing the LSTMs to the TCNs, we see that the TCNs get a slightly better performance. The difference was not big, but they get a slightly better performance. And for the TCNs, I saw no observable benefit after 7 samples. So I decided to further experiment with that configuration. So a certain amount of noise, TCNs with a length of 7 seconds using a binary data set. And now the average error is 2.05 meters, so it's lower than the GPS. And the root mean squared error is 1 order of magnitude better than the previous state of the art. Mostly because it is much more robust to noise because it captures many samples. And as you can see in this image, the color scale is slightly different, but if you look at the results, it's much better than the previous image, and you can get reliable positions whenever you have coverage. But now there are in fact 2 very big questions. So why would I want to use this instead of GNSS? Because up until now, I only talked about accuracy. I haven't talked about anything else. And does this work in practice? I'm working in a simulated environment, and in machine learning, there is a very, very big difference between simulated environment and practice. To answer the first question, we have to look again at the original model. And the most important question we need to ask is energy efficiency, because positioning is used in mobile devices, and mobile devices have a limited source of energy, at least many mobile devices. If you think about a car, that's definitely not a problem. But if you think about a smartwatch, that the positioning is a very, very big problem, the energy it uses. If you look at this diagram, there are 3 sources of energy consumption. Sampling, this is for the mobile device. I'm ignoring the base station now. Sampling the signal that is being received, transmitting the sample data to the base station, and receiving the position fix. I'm ignoring the last one because it's a very, very small piece of information compared to the other 2. And I'm assuming in the results that I'll show later on that I will use millimeter wave networks because this is a millimeter wave measurement. Therefore, the device also has millimeter wave capabilities, and millimeter wave devices, communication systems have a higher energy efficiency, which also helps with this process in general. Alternatively, we could skip the upload to the base station parts. This has a few drawbacks, but I see no objection in practice. If you decide to do this, the main sources of energy consumption is, again, sampling the signal, the same thing, running the inference in your mobile device, and downloading the machine learning model to your device. I'm ignoring the last part, assuming that you could do this in a certain region where you are often moving around. So we could have a more direct comparison, because the last one is a one-off thing and the other ones consume energy for each position fix. So if you put the numbers in perspective, the x-axis is the energy required per position fix in millijoules in a logarithmic scale. The y-axis is the average error, and the dots are the multiple measurements. So the dark green dot is the measurement where we get to upload the information to the base station. And these olive green points is when the inference is run at the mobile device. So for the dark green, it just sends to the base station and it doesn't know what's going on over there, it just receives the result. For the dark green one, the architecture makes an actual big difference in terms of energy consumption. The dark blue dots are the typical GPS. This point is for continuous measurement. So when you are doing a continuous measurement of your positioning with the GPS. And this point is when you are doing one position measurement per minute. So it is actually taken from the manual of a low power ship. So I'm comparing low power implementations. Remember again, the GPS has high power consumption modes of operation that can give you much more accurate predictions. You also have the military use case of the GPS, which is even better, but I'm comparing low power devices. This is my main concern for now. And for low power devices, getting sporadic measurements, it's still very expensive in terms of energy. Remember, X is in the log scale. And you have a big penalty for doing sporadic measurements in terms of accuracy. You also have this orange point, which is not used in practice, but it's contemplated in the assisted GPS framework. It has a similar scheme where you gather GPS information in your mobile device, you upload it to the base station, and the base station will do the actual signal processing. But regardless of where you look at, the thing I'm proposing, so this dark green point, has similar error, but is at least 50 times more energy efficient than the GNSS. So I hope that by now I've convinced you that this can be very good for low energy implementations. Another important detail is that this depends a lot on the millimeter wave network, and the results I've posted here in terms of energy are with respect to last year. And it is expected that the energy of efficiency of millimeter wave networks will improve a lot over time because it's a relatively new technology. So you can expect this point to go further to the left. And now the last question, does it work? I didn't have material to actually test it. However, recently in New York, the Mitsubishi Electric Research Laboratories implemented a thing that is very similar to what I proposed in a simplified environment, but still they have shown that this works in practice, both in terms of energy consumption and in terms of accuracy. So conclusions. There are two types of conclusions I want to make. First, the project specific. I know that many of you don't work in positioning, so I want to separate the conclusions. In terms of positioning, we know that millimeter waves brings new challenges, but also new possibilities. We know that beamforming can aid positioning systems because you are effectively increasing the spatial resolution. I have shown that the thing I proposed as state-of-the-art performance in millimeter waves for non-line of sight positioning. There are methods that are way better when you get line of sight, but I was concerned with the generalist case, and in generalist case, you'll be not in line of sight for a long portion of time. All this was achieved with a single anchor, so you need a single base station to make it work, and you don't need additional dedicated hardware. Most notably, you get GNSS-like performance at the fraction of the energy cost. And the generalist conclusions I want to take from this work is first, that a naive machine learning approach does not get you impressive results. Remember, I tried an MLP and it was an order of magnitude worse than the final results. So don't expect magic from a black box approach. You need to know what you are doing. And secondly, all the architecture enhancements and all the assumptions I made were through domain knowledge. So, there's a typo. You need to work with the problem expert in order to set the appropriate priors to your problem. So to modify your architecture, modify your assumptions, etc. And you can only get good results from ML projects when both parts, the ML knowledge and the domain-specific knowledge, interacts together. Thank you very much. In case you want to communicate with me, you have my email, and there is also a repository for all the work done here.
So thank you so much, João, for this really interesting presentation. We now have some time for questions. If you want to ask any question, you can go to the participants menu on the bottom and then a raise button hand appears on the bottom right, and I will unmute you. You can also ask questions through the chat. So in the meanwhile, I have a few questions. So João, could you please go to that slide where you show us the fingerprint? Yes.
This one?
Yes, that one. So could you explain a bit more what am I looking at? So what is the X and Y? I missed it a bit.
Okay. So the y-axis is the easiest to understand. It's the time domain. So in practice, you receive one column at a time. You build this one column at a time. And the y-axis from top to bottom is the time domain. So you are sampling power over time. And in practice, this whole thing, I think it's 7 microseconds. So it's very short. That's why you need a very high sampling frequency. And the y-axis is the different beamformed transmissions. So in each column, the base station is pointing at a different part of the space. And the color is the actual received power. However, I work with the binary signal.
Okay. So the beamforming part is on the transmitter or on the receiver, or at both?
It has, actually, that's a very good question, because it has to be done at both. However, the most important part is at the transmitter, which is what we are seeing here. At the receiver, we need to, because millimeter wave communications have a high loss, the receiver needs to sample the same transmission in almost an omnidirectional way. Otherwise, the position on, if you imagine a mobile phone, the position on which you held your phone would influence the position estimate. So to go around that problem, you need to sample the same signal multiple times so you can get an omnidirectional reconstruction of the signal, which is what I am showing. So under the hood, each column is sampled many times.
Okay. And my other question is there the possibility that, for example, that specific pattern that you're showing us corresponds to several different positions? So is there the is it possible that this is a many-to-one transformation, and that we can't reverse that in an univocal way, in a single
I think it
transformation?
is. I think it is. And the only way you could go around it is to add more resolution to the signal. So either in the time domain, sample at a higher frequency. If you sample at an infinite frequency, that would never happen, because different positions necessarily would have to see a different signal. But I think that is a problem. And if you do tracking, and if the positions are sufficiently away from each other, then it stops being a problem.
Right. Okay, because you have a certain confidence that if they are together, they are right.
And if they are together, it's not that big of a problem in practice, because the error would be small.
Right. Okay, so thank you. Those were my questions. We now have a question by Pankaj. So So I've asked you to unmute, Pankaj, so you have to unmute yourself now. Okay, so I think we're unmuted. You can ask your question if you. I'm afraid we're not hearing you. But you are unmuted. So if you're having problems with your setup, you can ask the question on the chat, and I'll read it. So in the meanwhile, are there any other questions? Okay. So when I can ask you to unmute yourself, that's I've muted everybody, and then if you want to ask a question, I ask you to unmute, and you have to unmute yourself. So okay, so here we go.
So one thing I don't understand is that how wide is the area where such a thing could work? Because you need a large capacity on the network to be able to work on a very large area, right? The GPS works anywhere. Would you have to download a new network when you go out of the area, or do you have a network with the, I mean, it will cover a country or a city?
That is a very good question. In practice, when I came up with this concept, I assumed that each base station would have their own dedicated model. And because 5G has a much shorter range of communications, you would need to train many models. So this is a big problem in practice because you would need to spend a lot of time training the networks. The best you can do to go around that problem is to do some sort of transfer learning. So assuming that the initial layers could be globally trained for the whole country or the whole world, and then do fine tuning of the last layers for each base station. I haven't looked into that problem.
But the training is okay because you do it only once. But when you move from base station to base station, you have to download the new model, right?
It depends on the mode of operation. So if I can show the slides. So in this mode of operation, which is what I am assuming, the model stays at the base station. So the mobile device would not see the change in the model as it walks around the city.
Oh, okay.
But if you work in this mode of operation, yes, that is a very serious problem. That's why when I propose the work, and usually all the papers I've done with this refer to this mode of operation, because I've faced a lot of struggle with reviewers because of that very same question.
Thank you.
Thank you.
We have a question through the chat. So the question is, with those reflections, how is the behavior indoors?
Indoors, that's actually a much harder problem, because outdoors, it could be the case that you don't have reflections. Indoors, you are pretty much guaranteed to have many reflections. However, each time there is a reflection, so if you go all the way back to electromagnetisms, there are coefficients, and each time a reflection happens for millimeter waves, you can expect that 30% of the power is lost. So in practice, it's very difficult to measure a signal when there are more than 5, 6 reflections. But yes, the problem is different indoors. And that's why in this presentation, I try to focus on the outdoors part, which is where I've worked towards to. However, if you go read this paper, they do most of their experiments indoors, which is slightly different, but you can extrapolate most of the conclusions between the two environments.
Okay, thank you. So I don't know if, is there any additional question? We do have one. So is it possible to describe the type of learning features?
So again, I'll have to go back to that slide with the beamformed fingerprint. So the non-tracking networks, the second third of the presentation, each neural network would have this input. When we are doing tracking, you have multiple copies, not copies, but multiple versions of the same signal. So let's assume the non-tracking case. These are samples of power, of the received power. What else can I say about them? This plot, it is very structured, but you are free to shuffle things around because you collect each point at a time, and there is really it is not mandatory to show the information like this. I don't know if this answers the question.
Hi, João. Thanks for your nice presentation. The question was raised by me, Rodolfo Priberam, from Institute of Telecommunications. My question is specifically because we have been using deep learning for modulation, detection of different modulations, and most of the times we are pre-processing the power, extracting more statistical features like moments, like and even sometimes joining together frequency domain and power and time domain in order to extract all these features and try to weight them and see their importance. But during the presentation, I was only basically oriented to the power domain,
Yes.
not power values over the time. So have you tried any other kind of information like pre-processing the power and obtain different statistic metrics in order to be considered in the learning system? Or you don't feel that they were necessary?
I think they would be helpful, and no, I haven't tried it. In fact, one of the jury of my CAT, so the thing we do at IST at the start of the PhD, suggested me to look into that. However, because I was getting good results and I kept having work to do, I actually never looked into that. But I think it will help a lot to have the channel properties. And this doesn't even consider any property in the frequency domain, for instance, which we know that contains a lot of information.
Okay, thanks. And thanks for your presentation.
Thank you.
So are there any further questions? Okay, so once again, thank you, João, for this really interesting presentation. And this is it for today, and I hope to see you all again in 2 weeks. Thank you.
Thank you, everyone. Have a good week.